All right, welcome to Unit 1.3. This is all about structural idealization. This is the idea that we can take a real structure and simplify it into something that we can analyze. Now, at first, it's going to seem very simple and very straightforward, but there is a large degree of subjectivity to this. And so, as the analysis or the structure gets more complex, this will certainly get more difficult to implement as well. So, it's good to keep that in mind. The learning objectives are to first discuss the idealization of members and connection types. So we're going to look at a few common ways that we do this in 2D. Then we'll have an exercise to practice this. And then we'll discuss the idealization of loads as well through concepts such as load paths and tributary area. And we'll have a simple exercise on this as well. And then finally, we will wrap it up with a comprehensive problem, which I'll leave for you all to solve. All right, so let's talk about idealization of members and supports. Let's take a typical steel frame building, and let's isolate one of the members here, a beam. So if we zoom into this beam over here, we see that it has an I cross-section, and it's got supports on either end where it's connected to girders. Okay, so first we start by simplifying this beam to a straight line, and then we need to think about how we will model each of these supports. Now, we'll get into detail a little bit later, but just by looking at them, we can see that they're fairly simple supports and are not going to provide a lot of rotational restraint, and so we're going to assume that these are pin supports, which we denote with triangles. Okay, so a pin support is going to actually provide two reactions, one vertical and one horizontal. So we'll label these as Rx and Ry, and we will call this X1 and Y1, and we'll do the same thing on the other side to denote that these are different reactions. So we have X2 and Y2. All right, so that would be one option. Now, if you remember back to the lecture on equilibrium, we know that we have really three equilibrium equations that we can use to solve for these reactions. And we have four reactions here, so we don't have enough equations to solve for all of the unknowns. So this is actually a statically indeterminate structure. But we could decide to make this statically determinate by changing one of the pins to a roller. So now we have three reactions, three equilibrium equations, and we can solve for those. Now, whether or not you decide to do this will depend on exactly what type of analysis you're carrying out. If you're primarily concerned, for example, with gravity loads, vertical loads, you can probably assume that the horizontal reactions are not very important, and so you can very easily get away with using a roller. But in other cases, you may get very different results if you make that assumption. So this is where the subjectivity comes in and can be a little bit tricky. So keep that in mind. All right, so let's talk about how supports will look in real life and how we can tell whether they should be a pin or something else. So we'll start with pins, and we'll look at two different types of structures, steel structures and concrete structures, because in practice, these look very different, even though in the analysis they will look identical. So it's good to form some comparisons here. So let's start on the left here with steel structures and examples of pin connections for these structures. So these are actually relatively easy. Most of the time they look like an actual pin. So here on the top left, we see that we have a pin-like support. This support is going to allow that column to rotate around that shaft, and therefore there is no moment restraint there, but it is going to provide restraint in translation in all directions. So that is an example of a very clear pin support. Another example of a pin support is this double arch structure here. This is a train station in Milan. And if we look at this support here, we can see that the structure is sort of converging on a very, very small point. Now again, we would not expect that structure to resist a lot of rotation, so we would expect that to be able to rotate around that point. So again, there is no moment restraint there. That's an example of a pin support. So how do we model a pin? That's at the bottom here. We have with a triangle, and like I said, we use two forces to model that, two reactions. A vertical reaction and a horizontal reaction. Of course, we are thinking about this in 2D. If we go to 3D, we'll have an additional reaction in the z direction, but we're not going to worry about that for now. All right. Now, concrete structures, again, this will look the same in practice, but this will look the same in the analysis, but in practice, we have to look at the reinforcement layout. So in this case, we're looking at the rebar. We can see that it's pretty much just a line of rebar. So if we push on it from the side, we can expect that rebar to rotate pretty easily around the base. And therefore, we don't expect this to have a lot of moment support. So we would expect this to be able to rotate in that direction. And so this would be an example of a pin for a concrete support. All right, so moving on, let's talk about the roller support. The roller provides only one reaction, a vertical reaction. And so some examples of that are rocker mechanisms in steel structures. So here we have a beam supported by a rocker. So the rocker is going to allow that to rotate. It's also going to allow it to translate left to right. There may be a little friction, but generally there's not a lot of restraint there. So that's an example of a rocker. We have also bearings, which are essentially a rubber type of structure, which again is going to allow this system to translate in one direction. Obviously, it's not going to allow it to move up or down. And it also doesn't provide a lot of moment support either, so the structure is able to rotate around as well. And so that's an example also of what we would consider a roller for analysis purposes. And then finally, we have actual roller-like mechanisms. You can see that this is, again, a beam sitting pretty much on top of a roller, and that's going to be able to rotate and also translate back and forth. In terms of concrete structures, we can also see roller-like mechanisms where you simply have a beam resting on a roller type, and we can also see bearings in much of the same way that we would see that in steel structures. These are very common in bridges, at the top of piers, where you're just simply supporting the deck. It's usually important to allow the concrete to translate laterally because it may be expanding and contracting due to thermal effects. So this is a very common setup for concrete bridge structures. All right, so the roller is very simple. The way that we model it is we use a circle, and we have only one reaction, and that is a reaction in the y direction. Okay. Now I will point out here that it's also possible for the reaction to go down, even though by the way it's drawn, it looks like the structure would be able to lift up, and in many cases in practice it will, with the exception of the bearing. But for analysis purposes, we have to be able to provide a reaction in both directions. So we will always assume that the roller has to stay tied to the ground regardless. Okay, so just keep that in mind. The reaction can be pointing down as well. All right, so the last type of support that we will think about is the fixed support. Okay, this support restrains motion in every direction. So in theory, that support is not allowed to rotate or translate at all. These are usually pretty beefy supports. So in the example of a steel structure, we may have a bolted end plate here that is deeply bolted into a concrete foundation. Okay, this is not going to allow either translation or rotation, and that would be a pretty typical example of fixed support. In terms of concrete structures, here are some columns. Again, you can see that the reinforcement layout is much more um, dense, right? And so we would expect that to provide more moment support as well. So the way that we model these fixed connections is through three reactions: a vertical reaction, a horizontal reaction, and a moment reaction. All right, so now let's move into member-to-member connections. We just talked about supports, which is a member to ground. Now we're looking at two members connected together. And again, in this case, we can also have pin connections. So for steel structures, here we have a column to beam connection, and we can see that this is a relatively simple connection. It's connecting the web of the beam to the column. So in case you're not aware of this terminology, the middle part of the beam is what we call the web, and the top or bottom part is what we call the flanges. Okay, so this is simply a connection at the web, and you can imagine that this will be able to rotate some around that connection, right? So that connection is only restraining the beam from moving up and down or left to right. We see these connections fairly commonly in real life as well. So you see here again, it's a web to web connection in this case. So pretty clear indicator of a pin connection. For concrete structures, again, we have to look at the layout. Here's a column, here's a beam. This is a relatively sparse layout of rebar that is going to allow some degree of rotation here. And so we would consider that a pin connection as well. So the way that the pin works or looks is we simply draw it as a little circle connecting two beam elements. And if we break it apart, we would get equal and opposite reactions in two directions. So let me make my beams a little thicker so we can tell what is a beam and what is a force. All right, so we would have, for example, a tensile force in this direction and an equal and opposite force in this direction, and then a horizontal force in the x direction and an equal and opposite force in that direction. Now keep in mind these will be equal, so Rx is the same for both and Ry is the same for both. The other type of member-to-member connection is a fixed connection. This is again one of the most common connections observed. These are again beefier connections between members. So here's again a column to beam connection, but we can see that we've beefed this up. We have a web connection at the beam, but we also have a weld at the flanges. And we have, on the column side, we have stiffeners, which again will make that column stiffer and not allow it to deflect too much around that point. In real life, we can see, again, welded connections here on the left. We can also see bolted end plates as well. That look very similar to what we saw for the fixed support, except now it's connecting a beam to a column, but very similar. So these beefy connections we will see generally when we have sort of a girder coming into a column or something like that. On the concrete side, we see a big difference in terms of reinforcement, right? So we observe that here we have a very, very, very dense reinforcement layout that's going to indicate that this is intended to be a moment connection. So you can see relative to the previous example, this is very dense. Okay. And the way that we model these fixed connections, again, we break it out, but now we have to include a moment as well. So we would have similarly a vertical reaction at both, again, equal and opposite, horizontal reaction, and then equal and opposite moments. All right, so that is it for connection types. Here is a summary of the connections and supports and their corresponding reactions with a little bit more detail, so showing a couple of other additional possible types of supports here and just the two types of connections, because it's very uncommon to see anything but these. And so hopefully these are illustrative and serve as a guide for you. All right, so let's actually take a look at some examples here. So here is an actual structure. It's a beam with two different support conditions and a load applied vertically. So the beam is going to be a line, and then we need to think about what A and B supports are. So let's start with A. We notice that it's, again, a very simple support. It's got just a web connection, and so that's pretty indicative that this is going to be a pin type support. It's not going to resist a lot of rotation. And then at the other side, it's essentially resting on another beam. And so we would expect that friction is not a very important form of restraint, so it's going to be able to move left and right. But obviously there is support up and down, and we would also expect it to rotate. So we're going to call this a roller, okay? And then we can't forget to draw the load, and then that load will result in three reactions. A vertical reaction at B, and a vertical and horizontal reaction at A. Here's another structure. This is a cantilevered frame, and let's go ahead and first draw the two beams. And now we have to again look at the types of configurations for the support at A and the member-to-member connection at B. So A has stiffeners in the corners there. That is meant to resist rotation, right? You're making that joint very stiff. And so this is clearly a fixed connection. And then same thing here at B. That is also a stiffener, so that is also expected to be a fixed connection. And so we would just simply leave it like this. Now, if we want to actually break this out and show the corresponding forces, we can do it this way. And so for a given load here, we would expect there to be both moments and horizontal and vertical internal forces at B. We need to make sure to draw the equal and opposite versions on the other side. And then we would expect to have also three reactions at A. Now, again, if we just think about this logically, A could be nothing but a fixed connection, because if it was a pin, this whole thing would just tip over and fall, which would be an unstable structure. We'll talk about stability a little bit later, but in this case, really, we have only one option to model this. Right, and here's a slightly harder example. We have a 3D structure. This is a wood frame house. However, we're just going to try to analyze the one of the frames. So we're going to look at just that frame there. And this one's interesting because it's got a truss-like structure up here, supported by 2 columns. Now, trusses, generally speaking, are modeled using only pin connections. So maybe let's start there. All right, so that's how our truss looks like. So we would expect each of these joints to be pins only. And now let's draw our columns. Okay, so let's worry about the column to truss connection last. Let's think about what the supports are for the columns. You can see that they're buried fairly deep into the ground. So we can assume that these will also resist moment. And so we can make these fixed. And then we have to think about how they're connected to the truss. Now, the connection looks relatively simple there. We don't see anything trying to stiffen that connection, so we could assume that this is pinned. And in fact, because the truss can only be modeled as pinned, we have to also account for that at the ends. And so really the only option here is for it to be pinned if we decide to model the top as a truss. Of course, we could decide to model it as a frame with fixed joints, but that would be pretty much overkill. So the more recommended approach here would be to use pins anytime you see a truss-like structure. So we would have, let's give these joints some names. So let's call this A, B, C, and D. So let's start actually with A. So we have 3 reactions at A, and then at B we have 2 internal forces, By and Bx, equal and opposite on the truss structure. And moving to C, again, pretty much the mirror image of that. And then finally D, mirror image of A. And exactly which way you draw these reactions is not really that important at this point. The only thing that is important is that when you have member-to-member connections, you do make them equal and opposite. Otherwise, you will get very funky results. But the exact direction doesn't matter. All right, so that is support and connection idealization. Now we're going to talk about idealizing loads. So loads in 2D, this diagram is showing how we want ideally loads to look like. And we have 2 different types of loads depending on the direction. So we call lateral loads that are acting horizontally on the structure, and gravity loads, those are acting vertically on the structure. And we can have within those two types of loads. We can have point loads and distributed loads, as we see here. And so we can have a lateral point load, or a lateral distributed load, or a gravity point load, or gravity distributed load. Now, there are actually many types of loads that engineers consider when designing a structure and analyzing it. The most common are the ones at the top. So these would be the self-weight of the structure, or what we call the dead load. And then loads related to people or vehicles, things that change over time. Those are what we call the live or service loads. Then we have loads related to the environment, such as wind, snow, and earthquakes. So you can think of wind generally being a lateral load, most likely distributed. Snow will be a gravity load, and that again will be distributed because it's spreading weight around. And then earthquake will be a lateral load. And this one is a little bit trickier. Not something that we'll cover too much in this class. If you're interested, I have a course on structural dynamics where we talk about this in much more detail. But this could be either a point load or a distributed load depending on how you choose to model it. Right? Then you have even more crazy loads like hydrostatic or soil pressure. These are generally distributed lateral loads. And then things like blast, fire, and impact. These are generally, blast and impact will be point loads, and fire will be really a thermal load, which will show up as sort of internal loads in the structure. We'll talk about thermal loads a little bit in the principle of virtual work unit, which is still a little bit of a ways away. All right, so what do we consider when going from a real 3D load to 2D? Generally, we like to look at things from a plan view, especially if we're thinking of a gravity distributed load. So we're going to look at the structural system directly from above. And from the floor plan, you can look at the locations of the columns, look at the spacing of the girders and joints, identify the load path, and distribute loads according to the tributary area principle, right? So this is a very important principle, which if you guys take away something from this lecture, I would like it to be that. Okay, so let's look at a typical floor plan. So the way, generally, if we're thinking about a building, the way that the load travels, typically we'll have a floor slab. That slab will be then supported by joists, which run in a specific direction. The joists will take that load to the girders, which then take that load to the columns. Okay, the spandrels function much the same as the joists, really, except they're just connected to the columns directly. So to see that a little bit better, let's look at an actual 3D rendering, and we'll talk about the idea of a load path here. So let's consider a single point gravity load on this system. So we have the point load on one of the joists, BF, that gets transferred to the girders, and then that gets transferred to the column. So the load path really is about sort of following the load as it gets transferred from one to the other. So let's start by drawing the joist, and we have a load applied at 6 feet from one end. And I'm going to skip the equations for equilibrium. You're welcome to try to solve these on your own, but I think this is a simple enough case where you can kind of see where the reactions come from without too much calculation. So in this case, if we just do a simple moment balance here, we can obtain the reactions. So we would have we have to do two moment balance and sum of forces in the y direction. If we do that, we'll get that the reaction at F is 3/4 of the load P, and the reaction at B is 1/4 of the load P. So that makes sense. The loads, the sum of the loads cancels out, and then the moments cancel out as well. The force at P is slightly higher, or actually 3 times higher, because it has a shorter moment arm. We know the reactions at F and B. That is going to be the loads on the girder, right? Which is, in this case, we're just going to pick one of the girders, EH, but obviously you could do this for the other girder as well. Okay, so now we have the girder EH. The load on EH is now the load at F. So we have a downward loads equal and opposite of 3/4 of P exactly at point F. Okay, and point F is 10 feet away from E. So now we do the same drill. We do sum of moments, equilibrium, and then equilibrium in the y direction. We would get 6/12 p reaction at E and a 1/4 p reaction at H. So we're just following this load down all the way to the column. So now we get to the column, and I don't really have joint labels for these, but let's look at the column at E here. So the top point is E. And so now we have 6/12 of P as the vertical load on the column. And there's no moment here, simply a gravity load. So this one's pretty easy. Equal and opposite at the bottom, 6/12 here. And actually, I forgot to simplify this down. Obviously, 6/12 P is just 1/2 of P. So excuse me for that one. So let's simplify this down. So 1/2 P, 1/2 P, 1/2 P. So that is load path. So we have followed a load P to F to E all the way down to the reaction at the bottom of that column, and that is 1/2 P. Right? Interesting, right? Because of where the P is applied, it means that half of the load is being held up by this column, and so presumably the other half of the load is somewhat distributed along the other column. So because it's not perfectly central, more of the load goes to that column. And notice it's not by coincidence that that is the column that is closest to P, right? So the closer P is to a specific point, we would expect more of that load to go to that point. So that brings us to the concept of tributary area, which is expanding this idea to distributed loads in a three-dimensional sense. All right, so let's look at the same frame, but now we have a distributed floor load in 2 dimensions across it. So that is 150 pounds per feet squared. Actually, this is a typo. Should be feet squared here. So because this is a area, the red part is an area. So we have a load per unit of that area. So let's say we want to find the loads on GC, right? So let's focus on that member for a moment. Okay, so ideally we can't use a 2D distributed load. We need a 1D distributed load. We need something that is in terms of pounds per feet. So we need something that looks like this. All right, so how do we get that? Well, we use the tributary area. We find the portion of this distributed load that can be attributed to GC. And the way we're going to do that is we're going to find the halfway point between the adjacent joists, and we're going to say that area is all attributed to GC. So because the distance between B and C and D is 10 feet, we're going to actually go half of that in either direction. So 5 feet and 5 feet in both directions. So that means that the tributary area here is 10 feet wide. So the way we calculate the distributed load on GC then is we would say, okay, we have 150 pounds per foot squared times 10 feet for the width of the tributary area, and that will give us 1,500 pounds per foot, a 1D load on GC. Now, if we're thinking about reactions at G and C, we can simply boil this down to an equivalent point load by just multiplying that W times the length of GC, which is 24 feet. If we do that, we get 36 kilopounds, or kips, 36,000 pounds. Since that load is exactly in the middle, then it gets distributed equally to G and C. So we have exactly half of that, 18 kips on each side. Now let's say we want to continue that to the girder EFGH. We now have to consider the load coming in from each of the joists, right? So FB and GC are identical because they're central, but HD and EA are actually different because they only get one side of the load. So the actual tributary area, let's say for HD, is only half of what it was for GC. So if we go ahead and draw EH, the girder, we will have 4 loads on it. The loads at F and G are going to be these 18 kip loads, but then the loads at the ends are going to be half of that. Okay, and then we could obviously solve for the reactions here using equilibrium equations, but for the interest of time, we'll stop there. This is already something that you should be comfortable with. The point here is that we have assigned an area of the distributed 2D load to each of the joists, and that enabled us to boil that down to a 1D distributed load and then a point load, corresponding point load, and then we follow the load path process as usual to do that. I will point out that the same idea applies to bridges. So if we take, let's say, a truss bridge with a deck, we can see that whatever loads are applied on the deck get transferred to the joists in the bridge and then to the actual truss. Actually, sorry. First, they get transferred to the joists, then the spanners here, then the actual truss structure, and then finally to the foundation. So we can follow either load path or tributary area ideas very similar to that. All right, so let's wrap all this up with just a quick example. I'm going to try to be more concrete here so you get an idea. So we're given a floor plan with the member areas shown as here. We've got now a weight for reinforced concrete and a weight for steel. So these are indeed pounds per foot squared because these are essentially densities of the material. And we're being asked to compute the dead load acting on beams CG, DH, AD, in column D. Now note that we are now considering both the dead load due to the steel and the concrete slab, which is 5 inches thick. Okay, and we're also given the area of the steel girder. So let's start with the girder side of the problem, so CG, DH, and AD. Right, the portion of the slab that is attributed to CG is here. This is the same as the other problem, so the dimensions are the same. We just have the added challenge that we have to consider the actual densities of the material rather than the distributed load. Okay, so the distributed load from the concrete, which we'll call RC, reinforced concrete, is going to be the density of the reinforced concrete times the thickness, which is 5 inches. Okay, so let's actually get this in real numbers. So 150 pounds per foot cubed. Let's turn inches into feet. So that's 5 over 12 feet. And then 10 feet stays the same. We get 625 pounds per foot as the distributed area. For steel, the process is similar. Call that WS. That is the density of the steel, which is 492 pounds per foot cubed. But now we've been given the area, which is 14.7 inches squared. We will convert that to feet squared by dividing by 12 squared. So 14.7 divided by 12 squared. That gives us feet squared. And that comes out to be 50.2 pounds per foot. All right, so we have effectively for beam CG two distributed loads on top of each other. The distributed load from the concrete, WRC, and the distributed load from the steel, WS. So these basically add together, and so we can take those, multiply it by the length of the joist, which is 24 feet, and we get a point load here that is P equals 625 plus 50.2 pounds per feet times 24 feet. That comes out to be 16.2 kips. Again, this is exactly in the middle, so we can say that the reaction at C and G are the same, and they're equal to 16.2 divided by 2, which is 8.1, and again, RG equals RC. All right, so that shows you one of them, CG. We still have DH and AD left. I'm going to leave these for you to resolve. The process will be very similar to what we did in the previous example. I will, though, however, give you a little tip also for the column, the D. Sometimes you can take a shortcut by doing different types of tributary areas. So if you're trying to find the force on column D, rather than following the load path all the way down, you can simply do a tributary area by column. So we can split the system like this evenly between columns and assign a tributary area to each column rather than each joint. And so the total load on D is going to be the sum of all the loads in that area. So we would essentially do a similar process where we look at the load due to the concrete, the load due to all the steel in that area, right? So we would have to essentially chop up some of those members and do it that way. And so, for example, we would get that the reaction at D would be 1/4 of the total weight of the concrete plus 1/2 of the total weight of girder AD, the joist CG, and the joist DH. I'll let you guys solve those numbers on your own, but that's the generic strategy there. Okay, so tributary area is flexible as long as you are dividing among the same system. In other words, joists, girders, columns. All right, so that is basically the end of the lecture. We have a comprehensive exercise, which I will leave for you all to do. This is sort of combining the concepts of idealization of structural members and tributary area, load path. So the idea is here's a real structure. It's a truss sign structure. The sign has a specific weight to it. The truss has a weight to it. The idea is idealize the structure in 2D and compute the reactions acting on the column. So think about this problem a little bit. It's got both a truss and a beam type. It's got distributed loads. Think about what strategy you would use to simplify this and model it. So in summary, the idealization process of simplifying connections and loads is, the goal of that is to get something that can be easily analyzed. We generally consider combinations of dead, live, and environmental loads. In this case, we've primarily looked at dead loads, but keep in mind that you could also have sort of a person or a vehicle on top of these structures. The load path is a fundamental concept showing how an applied load is transferred to the supports through each structural member. So make sure you understand that it's sort of a hierarchy of structural members, one connected to the other. And then the tributary area is used in 2D to condense a load into a 1D distributed load that, again, allows us to follow the load path principle all the way down to the supports.